Good morning, class. We are looking at the exam 3 review, covering section 3.5 through 4.2. The chain rule, implicit differentiation, related rates, derivatives of the log functions, differentials, maximum and minimum, and how derivatives affect the shape of a graph. First and foremost, let's remind everybody of differentiation formulas. You've seen many of them, and we have the definition, the basics, the product rule, the quotient rule, composite function, the chain rule, exponential and logarithmic rules. We add to it delta y, which is f of x plus delta x minus f of x, versus dy, which is f prime of x dx. And then at this point, when you come up with a tangent line, it's called L of x. Linearization refers to finding a tangent line, everybody. Logs. The base must be positive and it can't be 1. In that case, y equals log x base b is equivalent to x equals b to the power of y. You notice here they have the same exponent, the same base. If you look at this one and the arrow that I'm going to put on, b to the power of y equals x. And that can clearly give rise to all of these properties. Log of 1 is 0, regardless of the base. Log, when the base and the argument are the same, is 1. And these two refer to the fact that logarithmic functions, exponential functions are inverse functions. Product rule, quotient rule, power rule. Log of xy equals log x plus log y, same base b. That's the product rule. Log of x over y is log x minus log y, same base b. Log of x to the power of n is n log x, same base b. If we put log, that means the base is 10, common log, and we can see the transformation here. If we use ln, that means it's a natural log with the base e, and we can see the transformation here. Because the two functions, logarithmic functions and exponential functions, are inverse functions, therefore there must be symmetric with respect to the line y equals x. Here's the change of base formula, which indicates log x base b can be log x over log b with any base, for example, a. We either use common log x over log b, or natural log ln x over ln b for the sake of evaluation. And what this says is the following. We have the x-intercept at 1, 0. When x is between 0 and 1 here, ln x is negative below the x-axis. When x is larger than 1, ln x above the x-axis, and it's positive. That's all it says. You take the derivative of ln x, it's 1 over x. If it's g of x, 1 over g of x just by the same token, and g prime of x by the chain rule. If it has a different base, you tag along 1 over ln b. So for example, the derivative of log of f of x base b is 1 over f of x times f prime of x by the chain rule, and 1 over ln b by the change of base formula. Let's look at an example, and these examples come from either the lecture or the exam review that has been posted. I hope everybody knows where to find them. 2x plus y to the power of 4 equals x minus 2y, and we want to find dy dx or y prime using the implicit differentiation. This one, of course, 4 sits in front, 2x plus y cubed, the right side x, and times the derivative of the inside, of course, 2 plus y prime or dy dx. The right side x gives you 1 minus 2, y gives you y prime, and we are done with the calculus part. We are going to solve for y prime, and to do so, we are going to distribute this over 2. That means we want to multiply it by 2, and we get 8 times 2x plus y quantity cube, and then distribute it over this. And since we want to solve for y prime, we are going to move this one and make it plus 2y. And we want to move this one and make it negative. We are solving for y prime. So we are going to factor the y prime out. If I take the y prime out, I can take the 2y prime, but I'm interested in y prime. Gives me this blue part and this green number 2. And we divide both sides by the brackets, everybody. These brackets, put it underneath here. One thing I want to make a point of, so dy dx or y prime is 1 minus 8 times 2x plus y quantity cubed over 4 times 2x plus y cubed plus 2. If there's a common factor of 2 at the bottom, if there's a common factor of 2 at the top, you have to drop it as well. We want to differentiate this, and again, implicit differentiation. Sine y plus 2x cubed y squared equals 6. So the way we differentiated, we noticed that this is a product of two pieces. We put a raised dot there. And when it comes to sine, I'm going to remind you how I do the differentiation of trigonometric functions. I say sine and I pause. The answer is cosine. And of course, any trigonometric function requires an argument. So its argument is y, so cosine of y. And then y is like g of x cosine of y prime or dy dx. So I remind you, the derivative of sine is cosine. The derivative of sine of g of x is cosine g of x times g prime of x. So cosine y dy dx. And now 2x cubed times y squared, I'm going to write it as f times g, reminding everybody that we are going to use the product rule. Therefore, I get f prime, which is 6x squared times g, which is y squared, plus g prime, the derivative of y squared. Again, reminding everybody the derivative of g of x to the power of n is n g of x to the power of n minus 1 g prime of x. This is the extended power rule. Therefore, the derivative of y to the power of n, y acts like g of x, so n y to the power of n minus 1, y prime or dy dx. So the derivative of y squared is 2y dy dx times f, which is 2x cubed. The right side is a number. Any number results in 0 when you differentiate it. So we're done right here with the calculus part. Since we are solving for dy dx, first let's rewrite this class as 4x cubed y dy dx. We are not changing anything else. Second, let's move this and make it negative on the right side. And the other two pieces, these two, we will factor out the dy dx of y prime. This gives us cosine. This gives us 4x cubed y. Now, all you have to do, divide both sides by the parentheses. This goes away, and it becomes the denominator of the right side. Dy dx is minus 6x squared y squared over cosine y plus 4x cubed y. Find an equation of a tangent line to x squared plus 2xy minus y squared plus x equals 2. At this point, how do you find the equation of any line? You need a pair x comma y, it's given. You also need its slope. For tangent line, you find the derivative, you plug in, becomes the slope. Please understand the derivative is not the slope of a tangent line, it represents infinitely many. So let's do this implicitly. Starting with x squared, we get 2x. plus 2xy, you can either factor the 2 out and work on it or just the way it is. Notice that we put a raised dot here, and this is f times g, which uses the product rule. F prime is a 2, so this gives us 2x. This gives us 2 times g, which is y, plus g prime, which is y prime, or dy dx times 2x, and then minus y squared, just follow the extended power rule, minus 2y prime, and x gives you 1, 2 gives you 0. You're done. We can plug in here to find y prime numerically, and that becomes this one. But I like to solve for y prime. To do so, I'm going to move the following. This is going to move, becomes negative 2x. This is going to move, becomes negative 2y. This is going to move, becomes negative 1. On the left side, I'm going to factor out the y prime, and I get 2x, y prime times 2x minus 2y. The right side I'm not touching. And so y prime is the right side divided by the parentheses. Now, if I plug in, the pair becomes this log. So let's plug in. Right here, we have minus 2 times 1, minus 2 times 2, minus 1. The bottom is 2 times 1, minus 2 times 2. The numerator minus 2, minus 4, minus 1 is minus 7. The denominator is 2 minus 4, or minus 2. And the slope is positive 7/2. Y minus y1 equals m times x minus x of 1. That means y minus 2 is 7/2 x minus 1. And this gives me 7/2 x minus 7/2. I move the negative 2, make it positive 2. As you know, 2 is 4/2, with negative 7/2 becomes negative 3/2. Therefore, the equation of a tangent line y equals 7/2 x minus 3/2. The pair belongs to the original expression, also works out for the tangent line, and you can check it out, and it just tells you that this process was done right. We want to find dy dt for the equation x e to the power of y plus 4x equals y cubed, where dx dt is 2 and x equals negative 1 and y equals 0. The first thing I want you to notice, the moment you see this one or both, notice t is the independent variable, which means the derivative of y obviously is dy dt. The derivative of x is dx dt is no longer 1. So we are going to differentiate this by putting a raised dot in between and saying this is f times g and you use the product rule, f prime g plus g prime f. So x gives you dx dt not 1 times e to the power of y plus e to the power of y. Remember, any exponential, the answer is itself. So e to the power of g of x, e to the power of y. Then times g prime of x times the derivative of y is dy dt. For x, for dx dt. y cubed. Let's go back here is n y to the power of n minus 1 y prime or n y to the power of n minus 1 dy dx. So it's 3y squared, not dy dx, dy dt. Now, we can solve for dy dt, but over here you can just plug in and evaluate. Just plug in. When you plug in, you get 1 here, 1 here, 8 here, 0 here. So we get 2 plus and minus dy dt plus 8 equals 0. And this is 10. Moves to the other side, becomes negative 10. Minus dy dt is negative 10, so dy dt must be positive 10. Very simple, everybody. We want to differentiate this, and we notice that f of x is the product of 2x and ln of 3x squared. So we put a raised dot in between to make sure we understand that we are dealing with the product rule. Ln of 3x squared class, we can cut it into pieces, ln 3 plus 2 ln x, but it makes it more difficult just the way it is. We are going to go with f times g, the product. So f prime g plus g prime f. So f prime is a 2 times g ln of 3x squared plus g prime, the derivative of natural log. Flip this over. Times g prime of x, the derivative of the inside, the derivative of the argument of log is 6x. And then going back to the product of g prime f, f is 2x. And notice this doesn't change. This one is 12x squared over 3x squared is 4. So 2 ln of 3x squared plus 4. And we are done. Very straightforward, everybody. Again, we should know when to decompose a log. For example, right here, we must, because if we don't, we have to flip this over, then times its derivative, which requires a quotient rule. But if we cut it into pieces first, using the quotient rule number 6, everybody, and again, you can do it in one shot, but I'm going to show you 2 ways. First, use number 6, and it becomes ln of the top minus ln of the bottom. And then we use the product rule on this piece, make it ln 5 plus ln x. Now, please understand the last piece cannot be decomposed any longer, and it's done. So, ln 5 is a number. Its derivative is 0, but ln x gives you 1 over x. Minus natural log of x squared plus 5, ln of g of x. Flip it over, 1 over g of x, 1 over x squared plus 5. Then you need g prime, the derivative of the argument of log, which is 2x. And now we are ready to move on. Please understand, this is 1 over x. This is minus 2x over x squared plus 5, and x times x squared plus 5 is your common denominator. Therefore, 1 times x squared plus 5 minus 2x times x is the answer. And all we have to do is just simplify the numerator as follows. We are going to do just that. Let's go with, let's call it x squared plus 5 minus 2x squared, and these two add up to minus x squared. So y prime is negative x squared plus 5 over x times x squared plus 5. That is the final answer, everybody. G of x is log of 9 minus x cubed to the power of 4. We want to differentiate that. And the best course of action is to use the power rule first to take the 4 and bring it to the front. So if I'm differentiating this now, I just follow the log, 4 remains, flip this over. Because it's a function of x times its derivative g prime of x, so times negative 3x squared. And when the base is missing, that means the base is 10, that means common log. So 1 over ln b, 1 over ln 10. This is by the change of base formula. Putting it all together, the denominators are just a product of these two. The numerator is 4 times 1 times minus 3x squared times 1, which is negative 12x squared. And we are done. That's simple, everybody. Y equals f of x equals x squared over x minus 8. We want to find dy. To find dy, completely ignore it and find f prime of x, or dy dx. And to do so, I'm going to write f over g and use the quotient rule. So f prime g minus g prime f over g squared. So f prime is 2x times g, just write it x minus 8. Minus g prime, the derivative of the bottom is just 1 times f, which is x squared. And just write the bottom and square it, x minus 8 quantity squared. So we are going to distribute the 2x, and we get 2x squared minus 16x minus x squared. We can put these two together to get x squared. And that's f prime of x. That's not dy. So what is dy? The same thing times dx. The same thing times dx. dy is f prime of x dx. In second part says find dy and delta y when x is 4 and dx is 0.2. So first, for dy, replace the x with 4 and dx or delta x with 0.2. 4 squared is 16 minus 16 times 4 is 64. This is 4 squared, you get 16. We get minus 48. Divided by 16 is negative 3 times 0.2 is negative 0.6. And we're done with this part. Now, delta y is f of x plus delta x minus f of x. So f of 4.2 minus f of 4, that's elementary algebra, into the function goes 4.2. That's f of 4.2. Means 4.2 squared over 4.2 minus 8. Into the function goes 4, meaning 4 squared over 4 minus 8. Now use a calculator if you want. do it by hand, and you end up with negative 0.6421, which is pretty close to dy. And by the way, the smaller the choice of dx in a matter of comparison to x, the closer these two values. Section 3.8 differentials. Example 9, use differentials to approximate cube root of 63.5. Even if they don't mention differentials, that normally that's what it means. You have to use differentials or linearization or both. So the very first thing is we need a function. And to find the function, just read the question. You want cube root of 63.5. The operation is the cube root, so the function is cube root of x. So that's the function. The next thing is you want to choose an x which is close to 63.5, and you can find the cube root. The closest number would be 64 because cube root of 64, we should know by heart that is 4. And so now what is dx or delta x is the difference between the two is 0.5, but is it negative or positive? We are going to go from 64 to 63.5. So 63.5 minus 64 or minus 0.5, which means we know cube root of 64 is 4. We don't know cube root of 63.5, but negative indicates smaller than 4. On the other hand, for example, if we were interested in finding cube root of, let's say, 65, then dx would be 65 minus 64, which is positive 1. Again, meaning what? Meaning I don't know what is the cube root of 65, but it's larger than cube root of 64, so it's larger than 4. That's the meaning of it. Anyways, so with that being the case, we are going to go with f of x plus delta x equals f of x plus dy. We have f of x, but we don't have dy. We're going to ignore dy and find f prime of x. To do so, we're going to write this x to the power of 1/3. Differentiation 1/3 x to the power of negative 2/3. I'm assuming nobody has any problem with differentiation anymore. And therefore, you take this down, make it x to the power of positive 2/3 or cube root of x to the power of 2. We want dy. It's exactly the same thing times dx. So now we have the function cube root of x, and we have the dy dx over 3 cube root of x quantity squared. In other words, we find the function from here, we find the dy from here, and we are in business. Cube root of 63.5 means f of 63.5 means f of 64 plus 0 plus negative 0.5. So replace the x with 64 here and here, and the x with minus 0.5, and evaluate it. Of course, cube root of 64, everybody knows to be 4. And this one is 4. So this is 4. This is 4 squared is 16 times 3 is 48. And plus and minus, we're going to put minus 0.5 or 1/2. The reason I change it to 1/2, now it's a complex fraction. 1/2 over 48 means 1 over 2 times 48 or 1 over 96. And 4 minus that means 3 and 95 over 96. And I want you to pay attention to this number that we found, and there was no need for a calculator. This is an approximation. And the reason I have that, because I want to show you that if you go with a calculator approximation and you stop here, what happens? You have to round this to 6 because this next to it is 5. The same thing here. That's how close they are. The reason they are close, because dx, which is negative 0.5, compared to x is extremely small. So we are done. Again, I showed you this for a matter in a matter of comparison to calculated work, but this is what we get exactly. No need for a calculator. Now, linearization means find the equation of a tangent line. So you want to find the equation of a tangent line for what? For the function f of x equals cube root of x at what point? At x equals 60. So that's what you want to find. So how do you find it? First, you need a pair. You plug it in here. You get 64 comma 4. Then you need the slope. You plug it into f prime. If I put that here, so again, 64 goes into this one, gives me 64 comma 4. If you put it here, we've already done that. It gives you 4. Square root 16 times 3 is 48. So 1 over 48 is your slope. Y minus y1, that means y minus 4 equals m 1 over 48. X minus x of 1 means 64. And if you do the math, and I'm going to leave it for you to verify that L of x is 1 over 48, x plus 8 thirds, please check. And now, if I plug in 63.5, and again, I want you to do that, you get exactly this number, and I highly recommend it without the calculator. You will get this number, okay? Because you want to really verify it without a calculator. That goes pretty fast, okay? Linearization will give you the same answer as the differential. It is supposed to. Example 10, find the absolute max and mean values of f in the given interval. F of x is x squared minus 1 quantity cube, and the interval is negative 1 to 2. And remember the methodology, we're going to discuss it in a moment. But first and foremost, I want to tell you that if you are using this, you have to discuss the type of function and the domain of the function. So to remind you, all functions are continuous in their entire domain, meaning whatever function you deal with, if you can show what is the domain, in that domain, the function is continuous. So polynomials are in the form of a sub n, f of x equals a sub n x to the power of n all the way to a sub 0. This is the leading term, and a sub n is the leading coefficient, can't be 0. N is a whole number, the exponents. Whole numbers mean 0, 1, 2, 2, infinity. The domain for all polynomials is all real numbers, negative to positive infinity. And what is this? 2 times 3. This is a polynomial of degree 6. And because it's a polynomial, it's continuous in its entire domain of negative to positive infinity, makes it continuous in the given interval of minus 1 to 2. Therefore, we are going to go with the methodology and find the CPs. So we find f prime of x first. To find f prime of x, we get 3 times x squared minus 1 quantity squared times the derivative of the inside 2x. And we put these two together, we get 6x times x squared minus 1 quantity squared. So that's f prime of x. If you set that equal to 0, I hope you recognize this gives you 0. So this gives you x equals 0. This gives you x equals x squared equals 1, which gives you plus minus 1. And we have 3 answers. If a prime does not exist, gives you an empty set. Again, I'm reminding you this is phi, an empty set. You remember that? It's a Greek letter. This is phi. Okay, which represents an Empty set in set theory. And we look at those values. So there are three answers, and let's check it out. Is -1 in there? It's one of the endpoints. Is +1 in there? Yes. It's 0 in there? Right. So all of those, and I'm reminding you, all of those work and they belong. This is an element of, this is what we did in set theory. We read this as an element of the interval. So evaluate the function at those points. So for example, for -1, if I plug in here, I get -1 quantity squared minus 1 cube. And I hope you recognize that this is 1 minus 1, which makes it 0, and cube it, you get the same thing. If I plug in 0, again, for 0, I get 0 minus 1, 0 squared, which is 0 minus 1, which is minus 1. When I cube it, I get -1. I hope you recognize that 1, when you put it in there, works the same as -1, because when you square it becomes +1. So 1 gives you 0 also. And 2, if I plug in 2, I get 2 squared minus 1 cubed. 2 squared is 4. 4 minus 1 is 3 cubed. And 3 cubed is 27. So the largest value is 27. The smallest value is -1. So absolute max is 27. At this pair, 227, absolute mean is -1. At this pair, 0, comma, -1. So we write absolute max equals 27 at 2, comma, 27. Absolute minimum equals -1 at 0, comma, -1. This is the way we do the writing, everybody. Let's look at an example of a related rate problem. A small rock is dropped into a lake. Circular ripples spread over the surface with the radius of each circle increasing at a rate of 3.5 feet per second. Find the rate at which the area of the circle is changing when the radius is 4 feet. Remember, you're dealing with word problems. With word problems, you have to define your variables and know what you're dealing. So we are dealing with the circle versus the radius. So we should know the shape. We should know from the center to the circle is the radius. From the center to the radius to the circle, both sides is the diameter. Diameter is 2 times r. If we go around it, it's the circumference, just like a perimeter, 2 pi r. However, we are talking about the area equals pi r squared. So that's a piece of information from algebra geometry that you're supposed to know. And now let's write the rest of it. So a equals pi r squared. So what is given is that the radius is increasing at this rate. So that means dr dt. The moment you see the rate in calculus refers to the derivative. So dr dt is 3/2 feet per second. What are we looking for? The rate at which the area is changing. So we want the ADT. When do we want that? When the radius is 4 feet. So that's translation, everybody. So we are going to differentiate with respect to r, this function. And please understand, you want a, which is pi r squared. Now you want a prime of r, or dA dt. dA dt, which means keep the pi as a number, differentiate r squared, which is 2r dr dt. Okay, we are keeping the number, and now it's 2 pi r dr dt. Replace the r with 4 and replace the dr dt with 3/2. These two cancels out these two. We get 12 pi units of the area, square feet, over the units of time, seconds. And this is a better answer than this one. Depends on how they want you to answer it. This is in case you are using a calculator. They may ask you for that with a specific number of decimals. So you want to follow that. A spherical balloon is deflating, losing 8 cubic centimeters of air per minute. At the moment when the radius of the balloon is 20 centimeters, how fast is the radius decreasing? And hint, the volume is 4 liters per cube. By the way, the moment we use increasing, decreasing, then we don't have to worry about the sign. Positive means increasing, negative means decreasing, and we should know the volume is 4 liters per cube. So what is given? This one is given, meaning dV dt is 8 cubic centimeters per minute. Per minute. Even the units should sort of help you see what you're dealing with. So we want to see what's happening to the radius. That means dr dt at what point when the radius is 20 centimeters. So with that being the case, we are going to differentiate the volume with respect to t to get to dV dt. Therefore, dV dt is being calculated, and first we keep the 4 thirds pi and deal with r cubed, because 4 thirds pi is a number. So what is the derivative of r cubed? We put it here, 3r squared dr dt. And we get 4 pi r squared dr dt. We replace whatever we have, in this case dv dt with -8 and r with 20. By the way, you can solve for dr dt by dividing by 4 pi r squared both sides and then plug it in. Whatever is easier makes no difference. Now, of course, we are going to divide by this number. So what is this number? This is 400 times 4 makes it 1600, and then times pi 600, 1600 pi. This is a 0 plus 1600 pi, and 8 goes away, 16 becomes 2. So we have -1 over 200 pi. And the units of the radius over units of time, centimeters per minute. So -1 over 200 pi centimeters per minute. If you want to go with the decimal representation, you can. It's up to you, and you're done. Now, what does it mean? When the spherical balloon is losing 8 cubic centimeters of air per minute, the radius is decreasing by 0.001592. When you mention decreasing, then you don't write the negative sign. Remember that. All right, we want to graph f of x equals minus x cubed plus x squared plus x. And the idea is that besides using the information from algebra, we find relative extrema using f prime z equal to 0 and the sign graph. We find inflection point using f double prime, and then sketch the graph, just to remind you of what we did in the last session. So let's do that, okay? The very first thing, we want to graph the intercepts. And by the way, I hope you see that 0, 0 is one of them, okay? But if I factor the negative x out, I get x squared times minus x minus 1. So x equals 0 is one of them. And this one, I have to use a quadratic formula. When I said this equal to 0, the second part, with the second part, using the quadratic formula, for this part, everybody, for this part, because the first part is just 0, this is 0. For this part, A is 1, B is -1, C equals -1. We put it into the quadratic formula. And I'm assuming nobody has any problem with elementary algebra. 1, okay, minus B, so minus 1 makes it 1 plus minus the squared of B squared minus 1 quantity squared minus 4 times A, which is 1 times C, which is -1. This is +1, this is +4, we get that one. And therefore, the intercepts, one of them is 0, so 0, 0. And the other two are 1 plus square root of 5 divided by 2 and 1 minus square root of 5 divided by 2, comma 0. We can graph this by plotting those points, and we have the graph. You know, you've seen me doing that. So it can be done roughly, but we want to make it with more details. And that's why we are going to look at F prime and F double prime. Just a quick graph. If we were to do just from algebra and roughly 1 and square root of 5, that is that's about 2 point something, with 1 is 3 point something divided by 2, it's 1.6 roughly. And this one is roughly negative because you're subtracting that number, 0.6. And this is for the sake of graphing. So let's say we have 1 and 2, 1 and 2, 1. Okay. And so what happens is that let's use a different color. So this is 0, 0. Okay. 1.6 is almost here. Again, this is not to scale. And negative 0.6 is almost here. And if you look at this one, that's your leading term. Which says the graph has the end behavior in the second and fourth quadrant. So basically the graph looks something like this. It hits this point, then it has to come back up at some point, then it has to come back down at some point and hit this one. The thing is, we don't know when it's going to come back down or when it's going to go back up, and where is it that it's decreasing, increasing, you know, and all of the above. So, but I just wanted to give you an idea that it can be done that way. I'm going to erase this, and I'm going to go with more details by finding relative extrema, so going to F prime of X. So I'm going to erase this work, but I wanted to show you that even with pre-calculus, you should have an idea how it looks like. So we are going to find F prime of X, and to find F prime of X, it's easier to deal with this. Minus 3x squared plus 2x plus 1. Okay, and to factor this first, let me take the negative sign out. We get minus 3x squared. So minus 2x minus 1. And because 3 is a prime number class, makes it easier. So you write minus, okay, x and 3x, and because this is -1, you have no choice but to go 1 and -1. But where do you put them? You have to figure out such that the middle term works. Let me erase this part. That's what I want to keep. And please understand that this gives you -3x. This gives you +x. They must add up to -2x. They do. And if you set this equal to 0, you get x equals 1, x equals -1/3. Now we go with the first derivative test and the sine graph. So we go from negative to positive infinity, and we put these numbers that we have here, these two numbers, in order from smallest to largest. And we pick up test points. Okay. So to the let me just, TPs, short for test points. Over here to the left of -1/3, we pick -1. In between 0 is the easiest one. And after that, 2. And I want to again mention that the reason over here they will alternate, because if you look at f prime, this has exponent 1, this has exponent 1, they alternate. So if you plug in 0 and it's easier to use it here, you get positive. If you put it here, don't forget this negative sign. So 0 gives you positive 1. If it's positive here, the other two will alternate. Or plug in -1 and observe. So I'm going to throw in the arrows. Down arrow means the negative decreasing. Up arrow means positive increasing, decreasing. So as it changes from decreasing to increasing, this point, x equals -1/3, is the location of a local mean. You have to put it back into original equation to find the y-coordinate. 1 is the location of a local max. You have to put it into the original one to find the local max. So 1 is actually very easy. So this becomes 1 cube. This makes it negative. They cancel each other. And this becomes 1. So if you plug in 1, you get 1. But what about -1/3? Let's see. So the local max is 1 at 1, 1. But the local mean, we're going to plug in -1/3 to the power of 3. This is -1/27. This makes it positive 1/27. This is positive 1/9 minus 1/3. 27 is the LCD. So 1 plus 3 minus 9 minus 5/27 is your local mean at this pair. So you write local mean is minus 5/27 at the given pair. So the function is increasing here from -1/3 to 1 and decreasing otherwise, meaning from -1/3 to -1/3, union 1 to infinity. So increasing, where you see the plus sign, from -1/3 to 1, decreasing here or here, and we write it with the union of events. The next one is to find inflection points. So first, since we are going to go to the next page, I want to write the original function, f prime that we found, the intercepts, maximum, minimum intervals of increasing, decreasing. This is the information from the previous page. And now we're going to continue, but by finding f double prime. So I'm going to go to f prime and say it's -6x plus 2. Since we have to set it equal to 0, x becomes 1/3. So we are going to go with the sine graph x, f double prime goes from negative to positive infinity, and you put this number there. At x equals 1/3, f double prime is 0. We are going to use TPs, test points. So TPs, to the left of 1/3, the easiest point would be 0. To the right would be 1. And clearly there is only one critical point, and it doesn't have an exponent. They alternate. If you plug in 0, obviously to this one, you get positive 2. So if this is positive, this is negative, or you can put in 1 and see that it's negative. So that means the function is concave up here from -infinity to 1/3, and concave down here because we have a negative from 1/3 to infinity. That's the meaning of it. And 1/3 is the location of a inflection point. And if you want to find the inflection point, you have to go back to the original function and plug in 1/3. So we're going to say f of 1/3, that means negative 1/3 cubed plus 1/3 squared plus 1/3. As you know, this is 1/27. This makes it negative. This is 1/9. This is 1/3. Again, 27 is the common denominator. This is -1. This is +3. This is +9, with 27 being the denominator. They add up to +11/27, which means the inflection point has coordinates 1/3 and 11/27. We are ready to graph this, so we are going to write the summary. The x-intercept at 0, 0. Another one at negative 0.620. Another one at 1.620. The maximum occurs at 1, 1, and we put an arrow there because it's a maximum. The IP address. Now, the reason we change it to decimal because we want to see the location, okay? So 0.3 and 0.4, roughly here. Minimum, again, we're going to change it to this format because we want to see that. Negative 0.33 and let's say negative 0.2, it's here. Because it's a minimum, again, we put an arrow. And remember the leading term tells us the end behavior, as I mentioned, the second and fourth quadrant, and that's the graph. Very straightforward, everybody. Example 14, a 20-foot ladder leans against a building. I hope you remember that. The base of the ladder slips away at the rate of 2 feet per minute. Find the rate of change of the height of the ladder when the base is 12 feet from the building. We can't do this without drawing, okay? The setting has to be drawn and variables must be defined. So we have the wall or the building. We have the ladder moves this way, creating this shape. This moves down. The C or the ladder is fixed at 20 feet. As it moves this way, creates the speed or rate of 2 feet per minute. As it moves down, creates a speed, dy dt, that we are looking for. And we want to find that at the precise moment when the base, meaning x, if you don't have a drawing, which one is base, is 12 feet. Now, this one, we should know Pythagorean theorem that says a squared plus b squared equals c squared, and therefore we should know that. Of course, 20 squared is 400, and we are going to differentiate this one with respect to t. So what happens is that you have to relate the variables x and y together so you can find the derivative of one with respect to t and use the other one to find the answer. So this one is 2x dx dt. This one is 2y dy dt. This one is a number giving you 0. And I hope you notice that if you look at this one, you have everything except the y dt that you're looking for. You don't have a y either. However, since x is 12, if I plug in here, I should be able to get to the answer. $144, 400 minus 144 gives you 256. Take a root and you get 16 feet. So now we have everything. Replace the x with 12, dx dt with 2, y with 16, and find the missing dy dt. This is 2 times 2 times 12, 48. This is 2 times 16, 32. And so move the 48, make it negative, divide by 32. They are both divisible by 16, negative 3/2 feet per minute. Clearly, x is increasing, dx dt is positive, y is decreasing, dy dt must be negative. any of these.